Well, good morning, everyone, and thank you so much for coming. And please let me echo, first and foremost, it is so good to see people in person. I cannot tell you how much we've missed all this. So I'm delighted that you're all here with me today. As advertised, what I have for you today is a talk that I've named a medley of C++. Let me tell you a little bit about what my plans are. We all know about lightning talks, and we have some scheduled for this conference as well. But there are topics that simply aren't amenable to, 5-minute presentations. But there are also topics that just don't need a full hour. There's a claim that the term lightning talks was first coined in the year 2000, although the practice of lightning talks dates back farther than that. However, I'm old enough to remember at the first programmers conference I ever attended, a half-century ago. Doesn't that sound like an awfully long time? First conference I ever attended, there was an hour of short talks under the common title, What Every Fortran Programmer Ought to Know, rather grandiose title. But what I've planned today is in some sense an homage, because that talk was memorable, at least to me. In part, as I say, not every topic needs a full hour. So what I have for you today, as advertised, is a small collection of what I call mini talks, roughly in the style that I witnessed about 50 years ago, and of course with C++ rather than Fortran as the unifying theme. But then I had to come up with a title. So, I first thought of, well, that's not appropriate. So, sort of the obvious transformation. But that seemed too obvious, so I just chose the simpler, a medley of C++. So I propose to do four short talks, namely the ones I advertised, and then I will show you a short list of optional short talks. And if there's something in that list that appeals to any of you in particular, please choose, and those are the rest I will give in whatever time is remaining to us for a total of 90 minutes. So, the first talk I've titled The Universe of C++ Types. Of course. Please forgive a bit of whimsy. So, I think it's fairly well known that in C++ we classify our types. And these are enshrined into the language. They're also in the standard library under the name traits. Fortunately, they mostly agree. That's a good thing. It's important to keep in mind that the CV qualification, if any, does not affect the classification. So const int is classified identically to int, for example, okay? But let me start off by giving you a short puzzle, and I promise the answer will come at the end of this little short talk. For which classification of types, T, does this predicate yield false? Sorry, I went too fast. Take a careful look, take the type T, apply const, and then ask, is it const? For what kinds of types does it report false? All right, answer at the end. So the first major classification is known as fundamental types. And within the fundamental types, we first have the 4 void types. Yes, 4, because they can be CV qualified, right? So there are 4 of them. Similarly, we have the null-putter T types, occasionally spelled decal type of null-putter, right? I'm not sure why that has to be a library type, though. Seems the core language knows all about it already, but nonetheless, it's a library type. So like the voids, these have their own classification. Then we have the very important arithmetic types, which are subclassified. First, we have floating point types. And we're going to have some new ones in C++23, it looks like. For example, bfloat 16 looks like it's going to be in C++23. And then we have the integral types, also referred to as integer types. Those terms are synonymous in the standard. So let's talk about those, because there's a lot to say about them. Here's the start of the integer types. Bool and char are fairly well known. The rest, not known as well, but they're there. They're part of the core language. Then we have what are called the signed integer types, which are subdivided into the standard signed integer types, the list that we're all familiar with, and the extended signed integer types, which are specified as implementation defined, except I don't know of any implementation that does. And if you do, I'd like to hear of it, please. Analogously, we have the unsigned integer types, again, subdivided into the standard unsigned integer types and the extended ones. And again, I don't know of any of those. Okay, so that's fundamental types. The other half, more than half, are known as compound types because they rely on one or more other types. The fundamental ones stand alone. There's no other type that's used as an adjunct. The compound types rely on some other type. For example, we can have arrays, right? Well, you can't have an array without a type of the element of the array. Therefore, it's a compound type. And of course, arrays come in two flavors, depending on whether you do or don't know the extent, which in the library is referred to as bounded versus unbounded array types, okay, instead of known versus unknown. We have the two kinds of reference types, and they involve an object or a free function or some static member function of some specified type. And we have pointer types, subdivided into pointers to void or pointers to an object, free function, or static member function of some specified type. Again, that's why it's a compound type. Pointers are compound types. We then have function types, and those are compound types because you have types of parameters as well as the return type. But further, there's also a bool involved nowadays because there's a no except specification as part of the function type. Okay? And then we have types that are classes, which contain a sequence of 0 or more other types as members. We have enumerations, we have functions that are members, and we have a set of restrictions on accessing those members. And finally, to finish up the compound types, we have unions, which fundamentally are classes that can contain objects of different types at different times. Okay? Now, to stir the pot a little bit and add a little bit of confusion, there are types that are classes, and there are class types. And they're not the same thing. We'll get to that in just a moment, okay? The final piece of the puzzle, of course, are enumeration types, and we have two flavors of those, right? Scoped versus unscoped. Oh, wait, there's more. Pointers to member are also compound types. All right? Now, if you put all of that together, I believe I've done it correctly, there is a set of 16 traits such that any type we care to name will fall into exactly one of those 16 categories. And if I've done it correctly, this is the list. The ones I've coded in red are the fundamental types. The blue ones are compound types. Please take a moment and have a look. See if you can think of any type for which exactly one of these will not report true. I believe this is the complete list. And of course, there are traits that do combinations of various things. For example, is this an arithmetic type? Well, that's a compound trait, right? Because a float will report yes, and an int will report yes. They're both arithmetic types. But those aren't, arithmetic is not one of the 16 here. No. No, they will not both return true. Null putter is its own type, right? It is not a pointer type. It's not. Null putter does not have a pointer type. It has its own type, and it's not a pointer type. Okay? Yeah, that confused me a lot at first, but I've gotten used to it. Okay, so there are other ways that we can classify types, okay? These are sort of the basic classifications. This is just about where everything starts. But the standard specifies some composite type classifications, and I've already mentioned this one. It's a class type, not because it's a class, but because it's a type that's declared with what's referred to as a class key. And there are exactly 3 of those: class, struct, and union. Any type that we declare with one of those class keys is considered a class type. But a union is not a class. It's a union, right? It's distinguishable, separable. But they're both class types. So there are types that are classes, and there are class types. And although they overlap, they're not the same. In the standard library, we have a classification known as function object types, which I discovered is sometimes very much misunderstood. Any type that's a pointer to function is considered a function object type. You can call it, right? If I have a pointer to function, I can call the function through that pointer. It's callable, right? It's considered a function object type. I mean, a pointer is certainly an object, so it fits into this category. Also, this part I think is pretty well known. Any class type that has a call operator parens, obviously it's callable. So it's considered a function object type. But I find that it's less well known that if I have a class type that has no operator parens of its own, yet it has a conversion operator to, let's say, a pointer to function, I can call it. It'll convert itself to a pointer to function and then call through that pointer. So it's considered a function object type. Okay? We tend not to take much advantage of that, at least in my experience, but there are cases where it's incredibly useful. Okay? But then further in the standard library, we actually have a classification that we refer to as a callable type, which is all of these function object types plus pointer to member types, since we can call those. By the way, please notice, it does not say pointer to member function. It says pointer to member. Some members have function type and some have object type. In the standard library, we have a facility called standard invoke. You can invoke member data if you have a pointer to it. The library knows how to do that. And that's how, for example, how the ranges library does projections. Okay, very useful feature. It's been there for quite a while, actually. Many of us don't really take good advantage of that. So there are a few more composite type classifications I'd like to mention. There's a classification called Scalar Types, which encompasses, well, as you see, arithmetic, enumeration, pointer, pointer to member, and the null-putter types. Those are considered scalars, scalar types. There's a classification known as object types. Well, everything is an object type unless it's a function reference or void type. Everything else is considered an object type, right? This catches a couple of programmers every so often, people I deal with. They say, well, you know, I have this reference. I think, yeah, but that's not an object. It's not an object type. Yes, I know there's storage involved. It's not an object type. The language says so. Okay? There's a classification called incomplete types. And types can be incomplete for at least two different reasons. Some are born incomplete, like the void types. By definition, void is a type that is incomplete and cannot ever be completed. That's one of its defining characteristics. And of course, any class type that's been declared but not yet defined is incomplete. You can form a pointer to it, but you can't have an object of that type. I mean, ab initio, you don't know how much memory to allocate for it, right? It's incomplete. Also, enumerations, quote, in certain contexts are considered incomplete. And any array type where either the bound is unknown or the element type is incomplete, that array type is considered incomplete. Okay? Let me show you an example of how this kind of information is occasionally useful. This isn't the sort of thing that we would deal with typically on a daily basis, but knowing these classifications has simplified my life enormously over the past many decades. So I'd like to show you a small variant of what I've called the detection idiom. This is something I came up with not quite 10 years ago now. So imagine we have this primary template, and just off the bat, it's a variable template, of course, and we define it with the value false. So any type you care to name is complete at the moment reports false. But notice there's a second template parameter, a type parameter that has a default of size t. Okay? That's important. And here's why. If I provide a specialization, a partial specialization in this case, under this circumstance, the trait will report true. But only if the specialization is well formed. That's key. So when is this specialization well formed and when is it not well formed? Well, let's look at the sub-expression there, size of t. Size of t is well formed if and only if t is a complete type. The language does not allow you to get an answer to size of for an incomplete type. I mean, what would be the size of void? There's no size, right? The type is incomplete. You can't ask, what's your size? We don't know. It's incomplete. Well, if that's not well formed, then svine will kick in. And this specialization is silently discarded, as if it does not exist. And the only part that's left is the primary template, which will report false. Right? So if my type T is complete, the specialization is well formed, and it'll report true. If the type T is incomplete, the specialization is ill-formed, svine will cause it to be ignored, and the principal template will report false. So in a nutshell, this is sort of the canonical use case of what I termed the detection idiom. I have one small caveat in case you choose to use this trait. Be very careful with it, because there's a small risk. The risk is that the compiler could give you a different answer at different points in your program. For example, if you provide only a forward declaration, the trait will report false because it's not complete. If you later complete the definition and try the trait again, now you get an answer of true. It is complete. We as programmers are not allowed to do that. The language does not permit us to get two different answers to the same question. And you end up with an ill-formed program that the compiler is not required to diagnose. So you don't get a diagnostic if you violate that. So please be careful. That kind of inconsistency violates ODR and probably half a dozen other rules. Okay? So before I finish this little mini talk, it's time to answer the puzzle that I left you with at the beginning. If I have a type, I apply const and ask if it's const. The answer is false if my type started out to be a reference type or a function type. There are no const reference types. There are no const function types. You can apply const. That does not give you a const type. Standard language rules, been there for a very long time. Nothing novel about it, but not particularly well known, I've discovered. Now, I admit that this is perhaps not useful knowledge on a daily basis, but I'll give you an example of how much this kind of knowledge can save in certain circumstances. So you're probably all aware that there is a one-type trait named isFunction. Here's a type. Tell me yes or no, is it a function type? The traditional implementation of isFunction required a primary template and 48 specializations. Yes, 48 specializations. There's the math in case you want to double check. Because you've got to take into account CV qualifications, you've got to take into account reference qualifications, you've got to take into account no except nowadays, and everybody forgets about ellipsis arguments. Okay, those are part of function types too. 48 specializations. And everybody I know of who implemented this trait, wrote macros to just generate all this stuff instead of, risking leaving one out. However, here's a complete implementation of isFunction, taking advantage of this knowledge. Oh, and by the way, that 48 doesn't include non-standard calling conventions like Microsoft has. What do they call it? Something call. Yes, thank you. Okay, so you need even more specializations to take care of those, all right? So here's the complete implementation. No specializations, very straightforward. isFunction is true if the isConst does not report false, which means it's either a reference or it's a function. And if it's not a reference, it must be a function. I'm done. So, yes, classifications, not the most challenging piece of information, but boy, can it be useful. And with that, Thanks very much for part 1. Okay? I have time for 1 or 2 very quick questions if anybody has any right now. Otherwise, I want to make very clear, I'm very happy to take questions after my 90 minutes is up, out in the hallway or over lunch or something. Very happy to take your questions. Okay, so time for the second promised talk. The principle behind C++ declaration syntax. I gave an earlier version of this talk several years ago, and when I was finished, someone came up to me and said, I've written C++ parsers, and I never knew this. Of course, I wanted to say, why not? But that's a little impertinent. There are a lot of people who don't like the syntax of our declarations. And I can understand that. But I've discovered that most of us are very poorly taught how declarations work. We're usually taught by example. If you want an int, you do it this way. Okay, but it turns out there's a principle. So what is that guiding principle? Well, let me quote the master. The style used in expressions carries through to declarations. And for those of you who don't know the name, Dennis Ritchie is Mr. C. Dennis Ritchie devised the C programming language, to which, of course, we owe our ancestry. I knew Dennis, lovely man. Anyway, so what does this principle really mean? Let's talk about that briefly. Because the principle applies to us in C++. So let's just start a little thought experiment. Suppose I have some entity named X. Okay? What kinds of expressions could I write that involve X and that result in a value of type int? Let's just keep it very simple, okay? What could I write that would yield a result of type int? Well, here are 4 short examples. I could just write X, right? Simple variable gives me a value of type int. If it's an array, I write X with an appropriate subscript expression. If it's a pointer, I write indirect X. And if it's a function, I write a function call. Call X with appropriate arguments. Okay? So there's 4 candidates. So how would I declare those X's for those 4 cases? Well, if it's a simple variable, I write int X. If it's an array, I write X with brackets. If it's a pointer, I write indirect X. And if it's a function, I write, X with appropriate argument types. Check out the 2 columns, left and right. Right? So what are the parts of a typical declaration? Well, first we write a type, followed by an expression, which in this context is known by the standard as a declarator. It's okay to think of it as an expression, but technically it's a declarator. And you have to write it in some form that could give a value of the type you just wrote. And then punctuation. Often a semicolon, if you're going to keep going, a comma, and then you keep going, right? And that's your fundamental syntax, right? So they're the same 4 examples again. Oh, wait. In an expression, I can put parentheses. I can do that in a declaration. Most of us don't, but we could. And it's occasionally useful. It's occasionally mandatory. That works. That works. They're just expressions. I mean, declarators, but they're expressions. That works. Oh, and by the way, precedence applies even in the declaration. For example, just recall, if you would, that the call operator has precedence over indirection, right? Some people say it has seniority. There's lots of vocabulary here, binds more tightly. It has precedence. So if I'm writing an expression, the call operator claims its operands before the indirection operator even starts to claim its operands, because that's how precedence works, right? And that works in a declaration too. Okay? That's how similar expressions can give you different meanings. One of my favorite examples looks like this. If I write star P of something, the P is callable, and the result of the call is dereferenceable. But if I write something very similar, just by inserting parentheses, I get a different meaning, right? Now, Q is dereferenceable, and the dereferenced result is what's callable. Okay? Now, that's the expression version. What would this look like in the context of a declarator? Well, just about the same. Here, P has a function type. P is a function that returns something that's dereferenceable, and if dereferenced, gives us an int. But by inserting parentheses, now Q is dereferenceable, and the result of the dereference is callable, and the result of the call gives us the int. There's no new rule here. Whatever works in an expression almost always works in a declaration. And by the way, although some of us don't like to do it, it is not uncommon to have multiple declarators that share a common type. So you could actually do this. Now, in practice, I don't really see this very often, but this is legal. Here I'm declaring 1, 2, 3, 4 variables? Yes, 4 identifiers. Actually, if I'm going to do this, I strongly prefer to lay it out like this. I just find this a lot easier to read. About 20-some years ago, I came up with this kind of layout. It turns out it's been independently rediscovered a couple of times since then and has become known as, quote, the one true comma layout. The human eye is really good at seeing patterns when things line up. So I've taken to doing commas at the beginning. And it's just a lot easier, for me at least, to see what's going on. Especially for those of you who do metaprogramming, think about putting commas out front instead of way at the end where they're hidden. This is not, English language or anything like this. Commas don't have to go after. They go before or between. They're separators, not terminators. Anyway, that's a little bit off topic. You can actually even do this with class members. So you can declare something looks like this. I don't particularly recommend that you do this, but there are occasional uses for it because it just follows the ordinary rule. And we all write expressions all the time. And now we can just put it into a new context. Okay? This is kind of interesting. It turns out you can't always do that. Quote from the standard. There's the citation in case you care to look it up. A declaration with several declarators is usually equivalent to the corresponding sequence of declarations, each with a single declarator. I found that usually to be very interesting. Well, when would it not be? Well, not quite always. As soon as you get auto into the mix, right, this doesn't work. If you do it this way, you get what you expect. But you need the common deduction, right? And then there's this, which we obtained via C. If you have any choice, please never do this. This is awful. This is horrible. So here's a type named S, declared as a struct. And now I have two variables of type S, one of which is named S. Yes, this is legal, C++. Please don't do that. Okay, the name of the variable hides the name of the type. Yes, it really does. Okay, it's not the same as this. Because as soon as you declare the variable, it hides the name of the type, and now you can't declare the second one of the same type. But you can bring it back if you say struct S, and that's known as an elaborated type name. Please don't take advantage of that unless you absolutely have to. I consider it abominable, but that's my opinion. A couple more syntax options, right? Recall I said earlier, first you write a type. I didn't say you have to write a type name. So you can get by with something that looks like this. This defines a type, capital S, and immediately defines a pair of variables of that type. But if that's legal, it means, you don't have to name your type. So now I have two variables whose type I can no longer utter because I never gave the type a name. I mean, you can say decal type, you can play games, but, right? So this is legal. And there's still more things that, I'm not going to talk about in this short little talk. We have attributes and we have initializers, various sorts, and we've got the qualifiers, and we've got specifiers. I won't swear, but I think I got the complete list of specifiers, except it keeps changing, so I'm not 100% confident anymore. But please let me recap, and let me beg you to teach this to your colleagues and students. There is an underlying principle, and if we understand the principle and teach it, declarations become far more palatable. The style used in expressions carries through to declarations. We all understand expressions. It's bread and butter for us. So why do some of our, especially novices, occasionally have terrible trouble with declarations? They're rarely taught this principle. So I beg of you, please do it. By the way, the same principle applies to typedefs, classical typedefs. They work exactly the same way. If you ever have to write a traditional typedef, pretend you're declaring a variable, and then just write the keyword typedef in front. You're done. That's how typedefs work. They work just like variables, okay? Even though many of us prefer using declarations nowadays, we still encounter typedefs from time to time. So do something like this. Here's a variable PTF whose type is a pointer to function type, right? You see the extra parentheses in there? So PTF is dereferenceable, and the dereference result is callable. And when you call it, you get an int. But if I want an alias for that type, it's exactly the same with the keyword typedef in front. Right? The top line declares a variable, the second line declares a type name. That's it. They're otherwise identical. And of course, ever since C++ 11, this is equivalent to the using declaration. Now, there's a little bit more to the story because we live outside the C subset. Everything I've said so far originates with C. But C doesn't have any reference types. And C++ has no expressions of reference type. And I know programmers who find that surprising, but it's true. And here's the quote from the standard if you care to look it up. If an expression initially has the type reference to T, the type is immediately adjusted to T. There are no expressions of reference type. There aren't any. So you can't write a declaration following the same notion. So we have to adapt, right? So there's no operator that can produce a reference type. So what C++ did is we adapted the pointer syntax to declare entities of reference type. And the adaptation is simply to, use the reference, the ampersand or double ampersand now, in place of where you would have put a pointer. All right? And there's an example of the adaptation at work. And then we needed one final adaptation, right? Namely, C doesn't have a scope resolution operator, : : It's not part of C. And yet we need to use that when we talk about membership, member declarations, pointer to members, and so forth, right? So if I, for example, had a simple struct that looked like this, it has two members. One of the members has an object type, the other one has a function type, but they're both members. One happens to have an object type and one happens to have a function type. They're both members. All right? The object type, member B, has type bool, and that's an object type. And the member D has a function type. That's all. It's the only difference. But when we declare a pointer to member, we name both the containing class of which it's a member and the type of what we're pointing to. So if I'm pointing to member data, it looks like that. The member data has type bool, which is an object type. And if I want to point to the member function, I say I'm pointing to the member, and its type is function type taking float returning double. Happens to have a function type. Same syntax. Okay, and before I wrap this up, I have one final little caveat. Still not quite the complete story. Haven't mentioned the role of type aliases in declaring other entities. Haven't talked about reference collapsing, reference to reference, which is, you can't do that. Haven't talked about late specified return types or structured binding. I mean, there's more to the story. There's always more to the story. This is C++ after all, right? There's always more to learn. But please humor me one last time. We have a principle to guide us. The style used in expressions carries through to declarations. Thank you, Dennis Ritchie, and thank you all. Thank you. All right, so that's number 2. Number 3, a very little bit of history. I used to get asked this all the time. Yes, we like lambdas. We know what they are. Why are they called lambdas? Well, there's a story there. It's not a long story. So why are they named lambdas? Well, the story starts, yeah, why not alpha or sigma or theta or what else is popping up here? Okay. Yeah, we could have named them Muse. I don't know. It would have been amusing, right? Okay. Yeah, I know. Look, I can only tell these jokes in a group of people like us, right? Who else is going to get it? Okay. So we're probably all aware that we owe a lot to the people I've called the pioneers of computation. Alan Turing is well known. Emil Post is not quite as well known, but there are systems called post systems. We have Kurt Gödel, Stephen Kleene, whose work we use all the time, especially in regular expressions. Kleene is the one who came up with the asterisk. It's called the Kleene closure, or Kleene star sometimes. And Alonzo Church. Alonzo Church plays an incredibly large role, by the way. It's not well known, but both Alan Turing and Stephen Kleene were his students. Not a bad legacy. Less well known, we have Andrei Markov Jr. If you're thinking about Markov chains, that's not him. That was his father, Andrei Sr. But Andrei Markov worked in this area. Axel Tuohy, Bertrand Russell is fairly well known, Alfred North Whitehead, and Dana Scott, who is still living, by the way. What did these people have in common? Well, they were the early pioneers in researching what we refer to as the foundations of mathematics, because there was no computing in that era, right? There was calculating, but not computing. And over time, their respective work slowly merged into a branch of mathematics that nowadays we tend to refer to as computability theory. But Church's notation in particular became the foundation of the Lisp programming language, which is, as best I can determine, is the second oldest programming language still in active use. And it dates from 1958. Fortran is older by 1 year, I believe. Don't quote me, but I'm fairly confident that that's correct. I'm doing that from memory. I'm very fond of this quote, by the way. Lisp is today's equivalent of Latin. Educated people are supposed to have studied and forgotten it. Okay, that's by Peter Dimov. So in what's known as higher order programming, as I'm sure many of you know, a key ingredient is not only that functions are callable, but they are copyable. Okay? And that's novel for people who grew up in a procedural world. When you write a function, you don't usually have the notion of a function that sort of crawls around in memory at various places, which is what copyability would give you. But in higher order programming, we think nothing about making copies of function or of things that behave like functions, right? And function objects in C++ have always fit this description. They're objects, they're copyable. Okay? So as of C++ 11, we introduced, and this is a quote, lambda expressions as a concise way to create a simple function object. And again, there's the citation in case you want to look it up and see more context. And as I'm sure we're all familiar with, lambdas in C++ have been evolving ever since C++ 11. We keep tinkering with it and making them more flexible and giving them more features. And we're still doing that in C++ 23, which is coming down the pipeline fairly rapidly now, by the way. In fact, there are people who consider that the untyped lambda calculus, which is what Church's work has been known as, was the first object-oriented language. So where did the term lambda come from? Well, nowadays, And for a very long time, functions have names, but this was not always the case. As far as I can determine, it was Euler who was the first to name functions, 1734. We had functions before then, but they didn't have names. When Church did his work in the 30s, he used anonymous function definitions. And they looked sort of like this. Y hat, right? That function of y that is defined as 3y plus 1. The function itself doesn't have a name. It's a function of y, which is the parameter. We would call it the parameter. Namely, 3y plus 1. And he got that notation. Well, he adapted it from similar notation that was used in the book by Whitehead and Russell. They used it for class abstraction. He adapted it for function abstraction. Okay? 1930s. We're coming up on 100 years, people. And by the way, this is what I was taught as a first-year grad student. Anonymous functions confused the hell out of me. But I finally got the hang of it. Okay? It's still around. Now, in 1964, Church wrote the following, that when Church finally published his work, here's what happened. That caret, that hat over the y, the typesetter didn't put it on top of the y. We don't exactly know why. Maybe there wasn't enough space. Maybe he thought it looked ugly. We don't know why. But he typeset the caret to the left instead of above. And now, of course, it looks like a capital Greek lambda. And then in a later, I don't know if it was a reprint or another edition of the work or whatever, that got changed to lowercase. There's your lambda. Yes, that's why. It's a typo. Okay? Maybe. If nothing else, it's a heck of a good story, right? I believe it's true, but we have contradictory evidence. Dana Scott, who was a former student of Church, and by the way, was a Turing Award recipient, he told a different story in a talk he gave about 4 years ago. And you can find that talk online if you're interested. It is interesting, but it's not short. So what he said, I'm paraphrasing, of course, he said that he once talked to Church's son-in-law, John Addison, and asked the son-in-law, John, to ask his father-in-law why lambda. And Scott's story is that Addison wrote Church a postcard asking the question, why did you pick lambda? And allegedly, Church remailed the postcard in an envelope and wrote eeny, meeny, miny, mo. So, we're not sure, is the short version. But in either case, it is the case that Church's notations for functions and function abstraction did become known fairly quickly as lambda expressions. Church's collected work in this area has become known as the lambda calculus. It is still taught in graduate schools, as far as I can determine. It is important. It has long since been recognized as a universal model of calculation, of computation, that's equivalent in computing power to all these other models as set forth by people like Post and Kleene and Turing. Turing machines have gotten, the reputation as being the model of computation. But Turing machines don't provide more computing power than any of these other notations do. Some of them are kind of amusing in nomenclature. For example, the mathematician Two-Way, which is how his name is pronounced, I've been told. The system of computation that he came up with is known as a one-way system. So it's Two-Way's one-way system. I found that was kind of entertaining. In any event, that's my story, and I'm sticking to it. Okay. The next talk that I promised, I feel very strongly about this topic. And I find myself, I've given this talk a few times in various forms and formats. And I keep finding more information. And for some reason, I take this very personally. I don't know how well it's known, but at the time that I attended school, there was no computer science at the undergraduate level. So I ended up with an undergraduate degree in mathematics. Now, what I did was computing, but my degree as an undergraduate is mathematics. And one of the courses, which I believe was required at the time, that I worked my proverbial butt off was what turns out to be an incredibly important course. And the person I'm going to tell you about was nowhere mentioned during this course. I did not know about this individual for years. For years. Let me tell you the story. Professor Dr. Emmy Neuter. I suspect hardly anybody in the room has heard of her. A few. I'm seeing half a dozen or so hands. Turns out she's pretty well known in the physics community, but not so much in the math community, and very little in the computing community. Let me tell you her story, please. I've actually recently found a children's book about her. Scientists are a famously anonymous lot, but few can match the perverse and unmerited obscurity of the 20th century mathematical genius, Emmy Neuter. She preferred to use her middle name, Emmy. Her father was a mathematician. He was a faculty member. But Emmy was not allowed to enroll in university classes. There's extreme aversion to allowing women to study. I'm quoting, the academic senate warned that co-ed education would overthrow all academic order. A faculty member even said, thinking ahead, if we train women and someday they'll become faculty, what will our soldiers think when they come back and find they are required to learn at the feet of a woman? The mathematician David Hilbert had a famous reply. He said, I don't see that the candidate's gender is an argument against her admission. After all, we are a university, not a bath house. That's a translation, but I think it's a pretty good one. So Neuter was finally allowed to attend courses, but they made her ask permission from every instructor whose lectures she had to attend. Individually, one by one. Awful. So after she finally got the right to matriculate, she did earn a PhD in 1907. There were no faculty jobs open to women. So you know what she did? She worked without pay. Her family supported her. And then she was hired, after a fashion, by Hilbert at the University of Göttingen. But she had to give lectures under his name, and she still wasn't paid. She completed a second doctorate, habilitation, and then she was finally appointed to a faculty position under a special contract, Lehrbeauftragte für Algebra. She continued to teach as she produced papers and theories at a staggering pace, including a lot of work that was rarely acknowledged that she simply contributed to publications under her colleagues' and students' names. She developed a reputation as a fast talker, a stern critic, and a devoted teacher. And a decade later, she had to flee. She ended up at Bryn Mawr College in the USA and had ties to the Institute for Advanced Science at Princeton. They are perhaps best known as Einstein's home in this country. Yes, Einstein knew her. She knew him. Dr. Neuter is the most eminent woman in mathematics in Europe and has had more students at Göttingen than anybody else in the department, according to the president of Bryn Mawr College. According to her last doctoral student, Miss Neuter's methods of thinking and working were to recognize the unessentials and brush them aside. This was far from a superficial achievement. Keep in mind, we're coming up on 100 years since these events. The development of abstract algebra, that's my course that I was talking about. One of the most distinctive innovations of 20th century mathematics is largely due to her, in her published papers, in lectures, and in influence on her contemporaries. Neuter's theorem from 1915 is described as one of the most important theorems ever proved in the development of modern physics, possibly on a par with the Pythagorean theorem. Now, I didn't know Christopher Hill, but I did know Leon Letterman, who holds a Nobel Prize. If he hadn't retired at the time he did, Leon would have been my boss. And I got to know him. He just passed away, I think, 5 years ago or so. Great man. Headline, Emmy Neuter saved general relativity. Since 1915, general relativity, a new way of thinking about gravity, had captured the attention of physicists, but this new theory had difficulties which Einstein could not resolve. We would likely not be celebrating this theory were it not for Emmy Neuter, who at her prime couldn't get a teaching job in her homeland because of her gender. It was Neuter's theorem that provided the mathematical breakthroughs that general relativity needed to win over physicists. That's her work. Einstein's theory of relativity would not have been accepted without her work. She did the math that Einstein couldn't, or at least didn't. But Neuter is recalled by relatively few of us these days. Her mathematical originality was absolute beyond comparison. She changed the face of algebra by her work. She is the greatest woman mathematician who has ever lived, and the greatest woman scientist of any sort now living, and a scholar at least on the plane of Madame Curie. I'm impressed. I really am. After she died, as a result of complications of surgery, I'm sorry to say, the following tribute was published. Within the past few days, a distinguished mathematician, Professor Emmy Neuter, died in her 53rd year. In the judgment of the most competent living mathematicians, she was the most significant creative mathematical genius thus far produced. She's interred on the campus at Bryn Mawr University. This tribute by Einstein. He knew. One of her biographers summarizes it this way. In her 53 years, many spent bucking a system that impeded her pursuit of mathematics. She had an extraordinary impact on both algebra and physics. There's no telling what else she might have accomplished if society and fate had been more kind. Okay, so why am I talking about her to a C++ audience? What does her work have to do with C++20? I guarantee you it is crucial. It was she who taught us to think in terms of simple and general algebraic concepts. For Emmy Neuter, relationships among numbers, functions, and operations became amenable to generalization only after they had been reduced to general conceptual relationships. Okay, fine. In case you missed it, ta-da, ta-da, yes. The greatest thing in 20th century mathematics, see if you can figure out who says this. What was her idea? It was that you could separate concepts from implementations. You could just deal with concepts. So if anybody invented generic programming, she did. She realized it all. She realized that you could fully separate these two things. Her contribution needs to be remembered. I certainly agree. I hope you do too. Who said this? Alex Stepanov. Who, by the way, I don't think this is terribly well known, a magnificent historian of mathematics. He knows mathematics history better than almost anybody I've ever met. Brilliant. Quick wrap up. I discovered that Time magazine, doing some kind of mea culpa, has been issuing covers, faux covers, for the era in which they just didn't put women on the cover. So they came up with this one. Even now, the world still learns from Neuter, whose abstract principles are fundamental. So the short version is C++20 owes concepts to Professor Emmy Neuter. Her contribution needs to be remembered. Thank you. I hope my irritation didn't show through too badly, but I get really wrapped up in all this. Okay, so those are the 4 promised short talks. We have about 25 minutes left. Let me show you a short list of options that I am now giving you. If there is 1 or perhaps 2, possibly 3 that seem interesting, let me know, and I will give those next. Okay, everybody take another 10 seconds, look at the list. Okay. Anybody have favorites, or would you like me to pick? Totally up to you. Sorry? Expression categories. Oh, number 7, you mean? Yeah, okay. Sure, I can do that. And number 5? Okay. All right, let me do them in order then. I'll do 5 and then I'll do 7. Is that all right with everyone? All right, and then we'll see if maybe there's time left or maybe not. Okay. All right, number 5, a review of published code. I've never done this before in public. So for me, this is going to be a novel. A review of published code. Here's the background. A while ago, I read a blog post that started out posing a not terribly difficult problem, but it had the following form. It says, suppose you give me 2 ASCII strings having the same number of characters. I wish to compute the number of matching characters, where matching means same position, same character. Okay. The blog then said the conventional approach in C would look as follows, and then there was a block of code, which I'll show you in a moment. And then the blog says there's nothing wrong with this code. Okay. And I don't disagree. There may be nothing wrong with the code, with the algorithm. But it's my opinion, that the published code is not of what I would call publication quality. And I'm concerned about things like that. I read an awful lot of blogs, and I see a number of bloggers in the room. Yes, I read your stuff. I keep my mouth shut, but I read it. okay? So I'm going to show you the code that was published. But before I do, I beg of you, please don't go on a scavenger hunt looking for it, okay? It misses the point that I'm trying to make. I really have no wish to embarrass anyone. I don't think I will, but I don't even want to give the impression. I don't want to start any kind of code war or feud or, you can do it this way, you can do it this way, okay. No, not interested. Please accept this review as an opinion. And as always, when it comes to opinions, everyone is free to adopt, adapt, or reject. All right? Chances are there are people in the room who will disagree with me. I have no problem with any of that. I'm a big boy. You won't be the first person who's ever disagreed with me. Okay? One other thing to keep in mind. The point of the blog was to look at the initial algorithm and see what can be done to speed it up. That's not my point. Okay? It was an interesting analysis, but I'm not interested today in talking about comparative algorithms. That's interesting, but that's not my point today. Instead, I want to talk about code quality and about making small incremental improvements in the direction of quality code. Okay? So let me tell you a bit about my general approach to what we nowadays refer to as code review. And all of us, I think, in practice, assess code. At least we assess our own code. Maybe we don't do it formally, but we should, perhaps. So it's important to know how to go about assessing code. Well, I think most of you know that I used to be a teacher. So routinely, I would grade student programs. And my approach was always to look for reasons to give a better grade. It never started with the intent of, I'm assuming this is perfect and now I'm going to penalize you. I never liked that. That doesn't work for me. Okay? I don't want to nitpick. This is bad, this is bad. No. This is good, this is good, this is really good. All right? So I look for reasons to reward with better grade. So at the time, I had a rubric, and this is just a very rough outline. This was fully fleshed out 40-some years ago. All right? Student turns in a program, it doesn't even compile, it's hopeless. Sorry, this is not acceptable. If it compiles and runs, but say crashes or just doesn't give me the right result, you get a barely passing grade. It's a passing grade, but by the skin of your teeth, almost by courtesy. Okay? Can't count it toward your major. We expect people to be competent. Right? That's not competence. If it runs to completion and gives me correct results, you've demonstrated at least minimal competence, and then I look for evidence of further things that you've learned and done well. Okay? So that's just a rough outline. And I find that I go back to that general approach in assessing code. I look for things that were done well, and I just quietly shudder at the rest. Now let me show you the published code that I'm going to assess. It looks like this. I'm going to stop talking for 10 or 20 seconds. Just look at it and form your own opinion. Okay? The only thing I've done is edit it very lightly for a better screen display. Okay? But I've changed none of the keystrokes, except perhaps the spacing. Okay. One last reminder. Keep in mind this was intended for comparing algorithms. The code does work. What would you do differently? And what would I do differently? Okay, let me show you very small steps, very small steps. All right, first things first. Did you notice the type mismatch? Yeah, a few of you are nodding. Many of you are saying, what type mismatch? Well, look at count. Look at size t. Look at the return type. Oops, there's a problem. All right, so let's change the return type and make that a size t. That one's easy. Okay? All right, having fixed that, I've got a bug about indentation. I don't like this indentation. So I perceive an inconsistency that I want to fix to make this easier to read. So I want to indent the body of the if the same way the for is indented. Let's be consistent, you know. And I'm going to get rid of those unnecessary braces because braces suggest a complexity that's just not here. This isn't complex. Why do we need the braces? I know there are style guides that say thou shalt use braces. I don't care. Okay? If you don't need them, I don't use them. Okay? There's a reason for that. My screen real estate is precious to me. Okay? My vision is not the best. I want to use every available pixel. Okay? I can't read 62 lines on a screen. I don't think I ever could. Okay. So it now ends up looking like this. Next, there's a loop counter. It's got a bigger scope than is necessary. Okay? Scope is a big deal as far as I'm concerned. So let's reduce the scope. I'm going to do that by moving the definition to the initialization clause. And I never, ever, ever use I as a variable name. I've had too many bad experiences with fonts in which I can't distinguish a lowercase I from a lowercase l from a vertical bar, etc. Okay? I by itself is a really bad choice for a variable name in my world. Okay? I is worse. Okay. So having done that, K is perfectly good. What's next? There's copying going on for no reason. Absolutely no reason. Every time you use a post increment, there's a copy. Yes, I understand the compiler might be alighting it for you, but you're paying for the compiler to do that. Pre-increment and post-increment aren't the same. They have the same side effect, perhaps, but one gives you an L value expression, the other one gives you a PR value expression. They're not the same. They are not interchangeable. Okay? So always use pre-increment unless you have a reason to use post-increment. And if you don't yet see the copy, write your own post-increment function and try to do it without a copy. I don't think you can. You have to return the original value. There's a copy. Oh, well, my compiler knows how to do all this. Yeah, maybe. I agree. Maybe, probably, perhaps. Did you test it out with every possible compiler flag in every combination on every platform that you're interested in? I don't think you did. Okay? Don't rely on the compiler. You don't know what the next version of the compiler is going to do. Say what you mean simply and directly. That's a quote from Strunk and White, Rule of English Language. Say what you mean simply and directly. If it's a pre-increment, say pre-increment. If you have a reason for a post-increment, then use a post-increment. But you need a reason. All right, so I fixed that. It now looks like that. Now I have a problem with the loop. What's my problem with the loop? Well, what I want it to say is that I want exactly n iterations. It doesn't say that. All right? because as written, the exit condition says, not less than, which means greater than or equal to. And I want the exit condition to be exactly equals. I want exactly n iterations. I can't do that with a less than. Can't do it. Okay? I want that exit condition to be an equals. So let's fix that. By the way, if you were controlling this loop with, say, a pointer variable or an iterator of some sort, you would have automatically done an equals or a not equals in there without even thinking about it, because less than isn't applicable. Right? Why is this different? I think it's not. Okay? All right, now I want to improve the interface a little bit. This algorithm doesn't mutate the characters that are supplied, so I'd like to say so. All right? So it's not just char pointer, it's char const pointer. Okay? Minor tweak. Now I'd like to improve the names a little bit. Right? Count is sort of a generic name. It's not a horrible name, but it doesn't tell me what I'm counting. N doesn't tell me what, N what. And there are no bytes that are matching. There's nothing byte-oriented about this. Why is it named matching bytes? Right? There are no bytes in sight. So here's where I'm going to leave it for a bit. All right? I'm not done. There's more to consider, but it's an approach. And the way I'd like to leave it, I'd like you to think about this. Would you have done these steps? Would you have done them in this order? Is it worth doing? Or am I just blowing smoke? In any event, thank you. By all means.
You didn't const the size.
I couldn't hear you. I'm sorry. Didn't.
The size T?
Yes.
The end chart, you didn't put a const on it. I know. What's your view on that? Because you're not mutating it.
I understand. If I could generalize the question a little bit, when do you constify parameters by value in particular? We all constify if you take it by reference. We sort of do that routinely. Should you constify if you take it by value? And the answer is it's a private matter. It's not part of the interface. Whether you put it there or not, it's not part of the interface. If you want the extra security to guarantee that you're not going to mutate your copy of this value, then by all means put it there. But the caller doesn't need to know that. It's an implementation detail. So I consider that a personal matter. I would not put it in a declaration of broader scope, because it doesn't make any difference to the caller. It makes a difference to me as the implementer, right? The call doesn't change just because he knows it's not going to be mutated. It's call by copy. Sorry, what is the term nowadays? We say call by value. 50 years ago, this was referred to as call by copy value. Somehow we lost the word copy in the nomenclature, okay? When I was in school, this was termed call by copy value, all right? So it's an implementation detail, okay? All right, I have about 5 minutes left. I'm going to make a valiant attempt at squeezing in one more quick talk, if that's okay, all right? And I think expression categories was the request. So let's see how much of this I can get through. Value categories in the expression category taxonomy. All right, so simple intro, programming in machine language is replete with instructions that read and write memory addresses or register addresses. But the address is technically the key, or modeled as the key of a key value pair, right? You supply the key to the hardware and it goes into the memory and supplies the bits from the memory. That's a key value pair. Not a common way to regard it, I think, but I think it fits, all right? Now, those of us who write in languages like C++ and other higher level languages, we typically use symbols, sometimes names or identifiers, whatever the nomenclature is, instead of addresses. Because let's be honest, programming with raw addresses is painful. So we don't do it. This is why higher level languages were invented in the first place. Right? 60 years ago, we all programmed in machine language. I can still do it, by the way. It doesn't mean I like to. And the point is you rely on your translator, like your compiler, to choose the actual addresses and map the symbols to those addresses, laying out the memory and so forth. Assembly languages used to be called symbolic programming systems a long time ago. But of course, the important point is that addresses are just bits, just like any other data, okay? This was the major innovation that John von Neumann produced to give us the von Neumann architecture. Before him, computers had two memories, one for instructions, one for data. It's known as the Harvard architecture, popularized by Howard Aiken, okay, who was Admiral Grace Murray Hopper's first boss, when she was a lieutenant. We're talking pre-World War II. Okay, so in any von Neumann architecture, if you have bits that denote an address, you can't just inspect them and distinguish them from bits that just denote data. A bit is a bit. There's no distinguishing characteristic, right? So by themselves, the bits that make up an address might denote the source for a read or fetch from memory. It might denote the target for a write to memory. They might be the bits that are written or read, right? They're just bits. We can do whatever we want to with them. And the same bits can serve all of these purposes at different times. Okay? The context is crucial to the correct interpretation. The type, of course, is part of that context. I mean, C++ is famous for strong typing. But the value category is an equally important part of that context, right? The type of some bundle of bits tells us how many bits are involved, which of them are salient, and so forth. Whether you can subdivide those bits into elements or members, each with its own type, and things like that, all right? But the value category of that bundle of bits is what tells us whether we're dealing with an address or a piece of data. And more generally, whether those bits are suitable as operands for the operator to which we're binding them. There has to be a matchup there. Historically, we first got value categories in the programming languages called CPL, initially named Cambridge Programming Language, later renamed Combined Programming Language. It's an ancestor of C and therefore of C++. It used the nomenclature L value and R value for the first time. C never called it R values. They always said non-L value, but okay, fine. And of course, the classical example distinguishing between what's available for the left or the right side of an assignment, okay? The key is that it's an L value if and only if it has identity. That's central, absolutely bedrock central. Because that means we can use the L value as the key part of a key value pair to get stuff into and out of memory. Okay? Quick example. I've got a pair of variables, x and y. I can write x equals 3, and that's fine. The x is an L value, the 3 is an R value. And that's suitable for an assignment. But if I write something just as simple as x equals y, that's not okay as it stands. assignment needs an R value on the right. I've supplied an X value, an L value. So there has to be what has become known as the L value to R value conversion. And then it's fine. And that's the origin of the L value to R value conversion. Okay? Now you can apply this insight into an analysis of a couple of operators, and I'm going to have to stop here in just a moment because of time reasons. But I'm happy to continue this, one-on-one if anybody cares to after we're done here. But let me do one quick page of analysis along these lines. For each arithmetic, relational, and shift operator, I'm going back to C++ 98 right now for simplicity, okay? Each of those takes a pair of R values as operands and produces an R value result. Each assignment operator, including the compound assignments, it takes a modifiable L value and one R value as its operands, and it produces an L value result. And modifiable L value just means it can't be const. Okay? Increment and decrement, and I just got done mentioning this in the earlier talk. Each of them takes a modifiable L value operand. The prefix operators give you an L value result. The postfix forms give you an R value result. And that can be significant. Okay? All right. I'm sorry, my time is up. I don't want to keep you from your lunch. Thank you all so much for coming today. I'm very happy to continue this conversation after the talk, either over lunch or anytime in the hallway track. All right? Thanks again, everybody.